thank you, Massimiliano, for the introduction. Very nice. I will do a very pedestrian thing, and let me start with the disclaimer. The disclaimer is I have not contributed to stochastic thermodynamics much, but I'm extremely intrigued in it and following it for years. And I have the feeling that stochastic thermodynamics is tightly related to what I'm really interested in, and that's complex systems. And somehow the relation of statistical mechanics of complex systems and stochastic thermodynamics is somehow obvious, but it's not yet clear to me at all. So in stochastic thermodynamics, we're interested in effects that arise from small systems. And what I will do in my presentation is to motivate a little bit why I think in what sense complex systems are small. And that's maybe the first just observation or peculiarity. And another thing that stochastic thermodynamics is interested in is in averaging over trajectories in systems. And what we have been working on for a while is that we are interested in the question for which types of trajectories, for which types of processes, in particular path-dependent processes, is something like the maximum entropy principle valid. So I'll speak a little bit on this, and yeah, while I'm not really contributing to stochastic thermodynamics here, I'll try to make clear what my question is. In relation to stochastic thermodynamics and complex systems, and especially in a certain type of process that we are very interested in since a couple of years. Namely, these are processes that we call sample space reducing processes. These are processes which are dissipative driven systems which, if you don't drive them, they reduce their sample space over time. So they explicitly break local detailed balance. And one can formulate these sample space reducing processes in very simple toy models that are simple enough to be accessible analytically, and they're non-trivial enough so that you can study important or relevant properties like entropy, or you can do maximum entropy principle with them. I'll show you how that works. And the last piece of motivation why I chose this topic here is that it's almost exactly a year that Murray Gell-Mann passed away, with whom we have contributed, or with whom we have worked on some parts that I will show you, in particular in where does maximum entropy principle apply in path-dependent processes. So my question is how to compute systemic properties, macroscopic properties, macro variables of small systems, and how can stochastic thermodynamics help us making progress in understanding stochastic complex systems. So when is a system small? So it's not necessarily the number of particles that we're that has to be small. I consider a system small if the phase space volume that it can explore is small. So what do I mean by that? If you think of a coin tossing experiment, if you're tossing a coin n times or n coins one time, you have 2 to the n possible states. Yeah? This is sample space or phase space that is exponential in the number of degrees of freedom n. So if a system has many less states than this exponential number of states. Then I consider it small. Yeah, and the question is, I think it's really a key to understanding complex systems. How does a small phase space volume affect the physics of a system? That's a big question that's driving me for a while now. Many complex systems are small in this sense. They have a sub-exponentially growing phase space, meaning if you make them bigger, phase space is growing only very, very slowly. And let me mention that that if you have such a system, if you enlarge it in terms of particles or degrees of freedom, if the phase space is growing only very, very small, not exponentially, that's the important thing. If it's not growing exponentially, it might violate Shannon's composition axiom. What is the composition axiom? These are the Shannon axioms that you all know. So he's talking about this uncertainty measure S, and he puts 4 axioms, and if those hold, what you then get is what you then have is that the only possibility for this uncertainty measure S is this negative P log P, sum over all micro states I that are possible. So first axiom says that this measure should depend continuously on the probabilities. S has the maximum for equidistribution. If you add a new state that occurs with 0 probability, then the measure is unchanged. And the composition axiom means that if you look at the measure of a composed system, A and B, it's the measure for one of the subsystems plus the measure on the other subsystem conditional on the first subsystem A. That's a composition axiom. For most complex systems, which are often non-ergodic, they are evolutionary or co-evolutionary, path-dependent, have long-range interactions, etc. This composition axiom is going to be invalid. So we are asking, what if we take out this 4th axiom, if we just kill it? As a consequence, if you relax the axioms, your resulting uncertainty measure or entropy is going to be something a little bit more general. How does it change if we just don't ask for this 4th axiom? It's just a mathematical playing. There's no physics, nothing in it. So we could prove a theorem. So if we keep the Shannon axioms 1 to 3 as they are, and if we don't consider the 4th, we just assume that this measure, this uncertainty measure, or let's call it entropy, is a sum of a function G that depends only on P, on the probabilities. For such systems for which these 3 Shannon-Khinchin axioms hold, all of the stochastical systems can be uniquely classified by 2 real numbers, C and D. D being any number between minus and positive infinity, and C being a number between 0 and 1. These 2 numbers characterize the asymptotic behavior of this measure. And you can give such a measure, this entropy. We call it CD entropy because it's parameterized by these 2 numbers C and D. And what it is, it's not negative, not sum over all states of P log P. It's the sum over of the incomplete gamma function that has in its second argument the logarithm of the probabilities. This is just a mathematical fact. E is the base of the logarithm that's used. And yeah, so just keep in mind, we call this CD entropy. This is the incomplete gamma function. It's this integral over a power law and a power and exponential function. Here's a few examples. If you take different values of C and D, if both C and D is 1, you get the Shannon entropy, or Boltzmann-Gibbs entropy, whatever you want. If D is equal to 0, C anything between 0 and 1, you get what people call the Zahles entropy. If C is equal 1 and D is anything greater than 0, you get this entropy that has been called Antianodo-Plastino entropy, etc., etc. So there is maybe, I don't know, up to maybe 50 different types of entropies that have been, or entropy functionals, let's say like that, that have been introduced in the past, I don't know, 30, 40 years, in very different contexts. All of these entropies that have been proposed, here's a list of some of them, are asymptotic special cases of the CD entropy that I've shown you. So that's a remarkable observation, nothing more at this point. If you maximize this entropy, you get, for the different values that you can put for C and D, you get either the Boltzmann distribution, if C and D is equal 1, or you get the power law, or you get stretched exponentials for the things that I've given you, for the examples I've given you. Or if C and D is anything that's allowed, then you get typically distribution functions which are exponentials of Lambert W functions. Lambert W functions appear in many contexts, time delayed, differential equations, etc. So this is a function you cannot write down explicitly, but it's a solution to a simple equation. Okay, there is no other possibilities for systems that obey the first 3 Shannon-Khinchin axioms and for which the 4th, the composition axiom, is violated. Let's skip that. So how can that be related to thermodynamics? So far it was nothing of physics at all. If we require an entropy to be extensive, this relation that you see here of the entropy, or this uncertainty measure of a composed system, W means number of states of a composed system of A and B. If this is the sum of the entropy measures of the individual number of states of the subsystems, then if you require that this relation holds, you can relate C and D, these 2 numbers that characterize your uncertainty measure, to the volume of phase space. W is the number of states as a function of n. What is n? N is the number of degrees of freedom in the system that you have. And W prime is the change, it's the derivative, first derivative of phase space. So that's the change of phase space if you make the system larger. So there's a nice relation of C and D. Of course, this is not yet thermodynamics, nothing of this, but you see already the smell where this could go. So,
Stefan, maybe if you could start to wrap up, see if you want some questions.
Okay, wait a second. Yeah, I'm totally. Let me come to the maximum entropy principle. I need a couple of more minutes for this. So if we look, the very pedestrian view of what you mentioned before, the Jane's maximum entropy principle. If you have a coin tossing experiment, this is This is how you can arrange your experiments. If you toss the coin once, twice, 3 times, etc., the red things is the multiplicities, how often you get certain things, and the blue parts is the probabilities. Yeah. If you ask what is the likelihood of the histogram after you toss the coin n times, histogram is a combination of times k1, the coin produced a head, and k2 is how often it produced tail. Then this is the probability to find a histogram of a binomial process, is the binomial coefficient times the probabilities that we have. Q1, Q2 is the bias of the coin in this case. Yeah? So if you take a multinomial process, the probability of finding the histogram is the multiplicity, is the multinomial factor times the probabilities. It's all trivial stuff. If you want to find the most likely distribution function, you can take, that's just what we had, we take the logarithm of it and then take the derivative of it. What is the logarithm of m, of the multiplicity? You look at this, you see immediately that this is nothing but Shannon entropy. So you're scrolling once, and you see that this is the Shannon entropy. And if you want the most likely histogram, you take the derivative, and then this is, you can reparameterize your constraints in terms of, for example, energy. If you have a physical system, then this is everything related to the probabilities. This is the multiplicity term. Yeah. So what is telling you this is working for systems that are of multinomial statistics, following multinomial statistics, and should not be expected to be applicable to path-dependent processes at all. So what we found with Murray-Gell-Mann is that if we have certain processes that explicitly depend on the previous history of the system, the maximum entropy principle still holds if the multinomial becomes a deformed multinomial. A deformed multinomial, you just redefine definition of what the factorial means. You can show, I'm skipping things, you can show that by doing this, you're not getting Shannon entropy, of course, in your maximum entropy principle, but again, a CD entropy, where the second, well, D is equal to 0. So that's super amazing that you're finding this very, very different context than we looked at before. The same type of entropic formula. Okay, so I could give an example. We can really show that you can use this formula to, if you are given update equations that describe path-dependent processes, you can compute an entropy, you can maximize this entropy for any date in the future, and you recover and predict the correct distribution function and check with simulation. Okay, so I'm running out of time hopelessly. We have different types of entropy that we have to look at. We have to make this. We have to distinguish a thermodynamic entropy from a maximum entropy type entropy. That's the message. And we have looked at different processes which are path dependent, like Polya processes, or these sample space reducing processes, and computed the different entropies that I mentioned. So for the Polya process, the maximum entropy principle entropy that appears is of this type. The sample space reducing processes, this is a very funny entangled entropy. The extensive entropy is very different from those. So it's one of the things that are really amazing, and where we don't fully understand them, and where I hope and think that there should be a deep relation to stochastic thermodynamics. Let me make one final comment, and that's you can use if you study these sample space reducing processes, you find a maximum entropy principle and an entropy that's associated to it. So that's a thing that should give you stationary distribution functions. If you take this entropy to compute thermodynamic potentials like Helmholtz free energy, then you get, besides the expected terms, you get two additional terms. And that's, again, something that's very, very similar to what is happening in stochastic thermodynamics, where you get these additional potentials. So again, we have not made the connection yet. I finish with this. We should do that, and that's one of the aims that I would like to understand in the next time. Thank you. Sorry.